Hey, grade 11s. In our last lesson, we talked about how many particles were in a mole. We described the mole as a grouping, and it was a group like a dozen is a group. A dozen is a group of 12 things. A mole is a group of 602 hexillion things, 6.02 times 10 to the 23rd things. Let's talk today about how we measure that, because very clearly we don't count. So when it comes to measuring moles, there's a couple of ways we can do it. We can measure grams, which is also called molar mass. There's other names for it as well. It might be called the gram atomic mass, the mass of a mole of atoms in grams. It could be called the gram molecular mass, the gram of a mole of molecules. Or it could be called the gram formula mass. All of these things just talk about how much does 1 mole of a substance weigh. Grab your periodic tables and take a look at carbon for one moment. On the periodic table, you'll notice that the atomic mass of 1 atom of carbon is 12 AMUs, atomic mass units. It weighs 12 because carbon contains 6 protons and 6 neutrons in its nucleus. 1 atom is 12 atomic mass units. It's very, very tiny. But if I take 602 hexillion carbon atoms, 6.02 times 10 to the 23rd carbon atoms, it would weigh 12 grams. The mass of 1 mole of a substance weighs the same in grams as the mass of 1 atom of the substance weighs in atomic mass units. What would we do if we had a mole of hydrogen? Hydrogen is diatomic. Well, again, from our periodic table, we can see that each atom of hydrogen weighs about 1 atomic mass unit. So if there's a group of 2 of them, we'd find 2 atomic mass units per molecule, or 2 grams per mole per grouping of hydrogen atoms. We can use the same concept for other molecules as well. If I wanted to know how much a mole of carbon monoxide would weigh, on my periodic table I'd find that 1 carbon weighs 12 grams and 1 mole of oxygen atoms weighs 16 grams. Since carbon monoxide is made of 1 of each, 1 mole of carbon monoxide molecules would weigh 28 grams. Once we know the molar mass of a molecule or an atom, we can use our unit factor label method to transition between grams and moles. Let's continue using carbon monoxide as an example. We've already figured out that the molar mass of carbon monoxide is 28 grams for every mole. Now, when I say grams per mole, I'm assuming 1 mole. How much then would 2.5 moles of carbon monoxide weigh? Well, remembering our steps, number 1, start with what you know. We know that we have 2.5 moles, so that's the first thing that I'm going to write on my factor label line. We then draw a big long line and cut it off. This cutoff again means we're going to multiply. Put the units you want to get rid of on the bottom. I don't want the word mole, so I write the word mole on the bottom. Put the units you're solving for on the top. I'm trying to get to mass, and mass tells me that I'm looking to solve for grams. So I'm going to write the units grams on the top. Now the truth that I would put here is how much does 1 mole weigh? Well, 1 mole of carbon monoxide weighs 28 grams. Numbers that are on the top of the line get multiplied together. Numbers on the bottom of the line we divide. We don't have to multiply and divide by 1 because multiplying and dividing by 1 doesn't change anything. So 2.5 times 28 is equal to 70. Because the word moles on the top cancels the word moles on the bottom, they're gone, and my answer will be 70 grams. How about if I want to go in the other direction? How many moles are there in 50 grams of carbon monoxide? This time, what we know is 50 grams. Again, we start with what we know. So I'm going to put 50 grams on my factor label line, draw a big long line, and cut that off. Then I'm going to put the units I'm trying to cancel on the bottom. So I'm going to write the word grams on the bottom, leaving a space for a number. Put the units I want to solve for on the top of the line. The word moles will go on the top of the line. Again, what is true? It's true that 1 mole weighs 28 grams. This time we're going to divide. 50 divided by 28 is 1.79. Again, since the units grams on the top cancels the unit grams on the bottom, and the only units we have left are moles, we have 1.79 moles of carbon monoxide. Now, when it comes to measuring solid substances, measuring grams is a reasonably easy thing to do, and is by far the most common way of measuring things in our lab. But gases have a nasty habit of not wanting to stay on the scale. Sometimes students will suggest that we could put them in a container and then subtract the weight of the container, which works great except for gases like hydrogen or helium that tend to float off the scale with the container. So there is another way that we can measure the amount that is a mole. Because all gases, regardless of whether it's a small little gas like hydrogen or helium or a great big heavy gas like radon, take up the same amount of space at standard temperature and pressure. They take up the amount of space at 22.4 liters. So if a mole has 22.4 liters, how many particles would there be inside of it? Well, the answer is still 602 hexillion. Remember, a mole is just a grouping. We're saying that gases, the grouping of that gas takes up 22.4 liters. So there will be this many particles inside this balloon. Now, would 22.4 liters of any gas weigh the same amount? Well, of course, no, it would not. Some gases have very small molar masses. Hydrogen, for example, weighs 2.02 grams for every 1 mole of the diatomic gas, whereas radon weighs significantly more. How can I convert then between moles and liters? Here's a good example. What is the volume of 5 moles of oxygen at standard temperature and pressure conditions? Don't worry that we've said standard temperature and pressure here. That just tells us we're allowed to use that truth, that 1 mole takes up 22.4 liters. And it doesn't matter what the gas would be. So again, we're going to start with what we know. Here we have 5 moles as our starting point. So I'm going to write 5 moles on my factor label line, draw a big long line, and cut that off. I'm putting the units I want to get rid of on the bottom. I don't want my answer to be in moles, so I write it on the bottom. What units do I want? Well, I'm asking to solve for volume. So when I'm asking to solve for volume, I'm looking for the units liters. I'm going to write the units liters on the top of the line. What numbers make this true? Well, we know the truth that 1 mole is equal to 22.4 liters for any gas. So I put the number 1 beside moles and 22.4 liters. Now, our numbers are both on the top of the line. Remember, timesing and multiplying by or dividing by 1 doesn't change anything. So 5 times 22.4 is 112. The unit moles on the top cancels the unit moles on the bottom, and our answer comes out in liters of oxygen. 5 moles of oxygen would take up 112 liters of space. This next question is somewhat more challenging. It asks us what mass of gas would occupy 44.8 liters at standard temperature and pressure. The question gives us mass, which is grams, or asks us for mass, which is in grams, but gives us a starting point of liters. There is no truth that connects liters directly to grams. So we're going to have to change it to moles first. As always, start with what you know. We know 44.8 liters. I don't want the units liters, so I'll write that on the bottom. And I'm first going to change it to moles, so I'm going to write the word moles on top. We already have this truth that 1 mole of any substance takes up 22.4 liters of space. So beside the word mole, I write the number 1, and beside the word liters, I write 22.4. At this point, the units liters will cancel, and I'll be at the units moles. Oftentimes, kids want to solve at this point for moles and then use that to change to grams, and you're welcome to do so, but we can also continue on the same factor label line. Extending this line a little further and cutting it off one more time, I now want to get rid of the word moles and write it on the bottom and change it to grams, so I write grams on top. Where do these numbers come from? From our periodic table, we can see that every one nitrogen atom, 1 mole of nitrogen atoms would weigh 14 grams. So N2, diatomic nitrogen, would weigh twice as much, or 28 grams. 1 mole of nitrogens weighs 28 grams. Notice we always put the number 1 beside the word mole. Here now, moles on the top cancels moles on the bottom, and the units we're left with are grams. So we can actually solve this entire line in one fell swoop. Multiply any numbers you find on the bottom of the line, hit divide before any numbers you find on the bottom of the line, and hit equals when you run out of numbers. So 44.8 times 28 divided by 22.4 gives us 56, and the units left over are grams. Now, we don't actually have to do it in that order. You could also say 44.8 divided by 22.4 times 28. You could run it backwards, 28 divided by 22.4 times 44.8. It doesn't matter, so long as we multiply across the top and divide across the bottom. I'm hoping that after this lesson you understand that the term molar mass refers to how much a mole of a substance weighs in grams. I hope you can calculate the molar mass for an atom or a molecule by adding up the bits from the periodic table. And then, can you perform conversions between moles and grams using our unit factor label method? I also need you to remember that the term STP stands for standard temperature and pressure, and it allows us to use the relationship between moles and volume. 1 mole of any gas takes up 22.4 liters of space. Then you should be able to use your factor label method to do conversion between moles and liters. There's a lot more that you can read and to get extra practice in your textbook on pages 326 to 340. Also, in your workbook, there are plenty of opportunities to practice on pages 29 to 32. Of course, you don't have to do every question right now, but I hope that you do enough that you understand how to make the conversions between grams and moles, and also between moles and liters.